In the last lecture, we talked of collisions between particles. We saw various cases where the two particles of equal mass collide, where a light particle collides against a heavy particle, or where a very heavy particle collides against a light particle. We have seen these cases, and we have studied also the collisions in a plane, and we have given the example of the billiard table, where all the balls have the same mass, and when they move at right angles to each other. Today, in this lecture, we are going to take up the concept center of mass. Center of mass, I think, is a very important topic and not difficult, but you need to understand it so that you can apply it whenever needed. So, this topic of center of mass, first of all, let us say, why do we need a center of mass at all? You see, whenever we consider the motion of a body, we generally deal with it as a point particle. You would remember, we always take point mass or point particle, because it is easy to calculate their state after a certain force has been applied or after they collide with something else. It is easy to calculate. Therefore, we think of them as mass particles or point masses, but point mass is only an idealization. In real life, there are no point masses. Even a small body, you would remember, contain a large number of particles. So, therefore, we have to take this fact into account and then proceed. When the size of a body is small compared with the relevant dimensions of the system, the body may be considered as a point mass for studying its dynamics. What it means is this. Let us take examples. For example, you are studying motion of the earth around the sun. In that, you can consider the earth as a point particle or a point mass. Why? Because the size of the earth is small compared with the dimensions in which the whole phenomenon is being considered. Motion of stars in the galaxy in a similar way can be considered as motion of point particles, because the size of a star is extremely small compared with the size of the galaxy. A cricket ball is not small, but when you consider its trajectory in a field of cricket or something else, then it becomes small compared with the relevant dimensions, and it can be considered a small point mass. However, when we consider the motion of the earth on its own axis, then we cannot consider the earth to be a point particle. It is then that we have considered the earth to be an extended object. When we consider the motion of an extended body, it is desirable to have a point in the body at which the whole mass of the body can be supposed to be concentrated. It then becomes easy to study the response of the body to external forces and torques. It is possible to define such a point. We call it the center of mass. I have read it, but what it means, let us see. I will try to explain to you what I mean by the center of mass of a body. Here is a body on which these forces are acting, F1 and F2. This is an extended body. If I want to study the effect of these forces F1 and F2 on this body, I look for a point in this body so that I can study the effect of these forces at that point, and the effect would be the same as the effect on the whole body. That is the meaning of center of mass. That is, the whole body can be replaced by a single point at which the whole mass of the body is concentrated. You see the second diagram. This point is the center of mass, and I can assume that the whole mass of this body is concentrated at this point, and I can study the effect of forces F1 and F2 acting at that point. Their effect would be the same as the effect of these forces on the extended body. That is the meaning of center of mass. Let me make it clear once again. I have an extended body here. When these forces act, there are millions of particles in this body. I do not know how to calculate the effect of these forces on this body. we will have to write millions of equations and solve them. That is not what we want. So, what we need or what we desire is a point in this body where I can assume that the whole mass of the body is concentrated at that point, and then study the effect of these forces at that point. That is the meaning of center of mass. That is, I have replaced whole body by just one point where the mass of the whole body is concentrated. That is, that point is called the center of mass of the body. So, let us now formally define the center of mass. We have two particles here, m1 and m2. Their position vectors referred to certain origin are r1 and r2, and the center of mass is somewhere between m1 and m2, and the coordinates of the center of mass or the position vector of the center of mass is capital R, RCM, and the coordinates of RCM are, or the position vector RCM is m1 r1 plus m2 r2 divided by m1 plus m2. And in terms of x axis, y axis, z axis, xCM, the x coordinate is m1 x1 plus m2 x2 divided by m1 plus m2. Y coordinate of the center of mass is m1 y1 plus m2 y2 divided by m1 plus m2, and the z coordinates of the center of mass is m1 z1 plus m2 z2 divided by m1 m2. For a system consisting of a large number of particles, this equation can be generalized. That is, the position vector of the center of mass is RCM is equal to the sum of mi ri, that is m1 r1 plus m2 r2 plus m3 r3 plus m4 r4 and so on. So, the sigma mi ri denotes the sum divided by sigma mi, where mi are the masses of particles, and since sigma mi is the total mass, therefore, it becomes 1 by m times sigma mi ri vector. That is the position vector of the center of mass. Let us take an example. m1, m2 are here shown, and center of mass is also shown. The x coordinate of the center of mass is xCM given by 1 by m mi xi, that is m1 x1 plus m2 x2 and so on, and yCM is 1 by m sigma m1 y1 and sigma mi yi, and zCM is 1 by m sigma mi zi. So, these are the x, y and z coordinates of the center of mass. If all the particles have the same mass and the total number of particles is n, then capital M is equal to small m times n. Small m is the mass of each particle. So, capital M is equal to small m into n, where n is the number of particles, and we replace this in our equations for the position vector of the center of mass, and we get that the position vector now can be written as 1 by n times sigma ri. Likewise, the x coordinate can be written as 1 by n sigma xi, y coordinate 1 by n sigma yi, and z coordinate as 1 by n sigma zi. If there are two particles only, let us see what happens. Two particles have coordinates x1 y1 and x2 y2, and they have equal mass, therefore, mass goes out of the equation, and the center of mass now, the x coordinate is just half x1 plus x2, yCM is half y1 plus y2, and zCM is half z1 plus z2. This means that the center of mass lies midway between the two particles. Remember that these two particles have the same mass, and therefore, the center of mass is at the center of these two particles. We can extend this definition. If a body consists of particles of the same mass and is geometrically regular, then the center of mass of that body would be the geometrical center of that body. Geometrical center of this cuboid is here, center of mass, geometrical center of this cylinder is here, of the sphere is here, and of this shape the center of mass is here. The idea is that the center of mass of regular bodies consisting of particles of equal mass lies at their geometrical centers. Now, let us consider a linear system of two particles. and suppose one particle has twice the mass of the other particle, then we can use our equations and we can get xcm is 1 by 3 times x1 plus 2x2. That is, x1 is the coordinate of particle 1 of mass m, x2 is the coordinate of the second particle with mass 2m, and xcm is 1 by 3 x1 plus 2 x2. You can remember that when the two masses are equal, the xcm was at the center of x1 and x2. Here it is 1/3 x1 plus 2 x2. It has moved towards x2, that is towards the heavier particle. So, center of mass moves towards the heavier particle. Where is the center of mass of the sun and the earth? Sun is very heavy compared with the earth, very highly massive compared with the earth, and therefore, we expect their center of mass to lie very close to the center of the sun. In fact, if you calculate, you can see that it lies very close to the center of the sun, inside the sun. Let us take another check. We have 3 particles here on this grid, and they have their coordinates. For example, this particle has x coordinates 5, 1, 2, 3, 4, 4, and y coordinate 3, and so on. There are 3 particles, and if you calculate their center of mass, it would be this dark dot. Coordinates are 1, 0. If you change the distribution, if you take the masses now at other points, the same masses, the same particles, but now their coordinates are different, and therefore, the center of mass now lies at a different point. The coordinates are 2, 1. What does it show? It shows that the center of mass is a function of mass distribution in the body. It is not a fixed thing. If mass distribution changes, then the center of mass also changes, as shown here. And what is the importance of center of mass? We have already discussed. This whole body can be replaced by just one point, the center of mass, and the effect of this force on this body can be studied or calculated. So, let us take now a rigid body, and suppose a force F produces on an acceleration ACM in the center of mass of that rigid body. Then this force can be written as mass of the rigid body into the acceleration, that is ACM, acceleration of the center of mass. And if there is no force, then F is equal to 0 and ACM is either 0 or constant. That is, the center of mass is either at rest or moves with uniform velocity. So, if we have a rigid body and there are no forces acting on it, its center of mass stays constant, or with respect to some frame it moves at constant velocity. Similarly, the momentum, if the center of mass moves with the velocity vcm, then its momentum is p, which is given by the mass of the rigid body into the velocity of the center of mass. And once again, if p is 0, you can see that vcm is either 0 or constant. Here I have shown 2 frames, inertial frames moving with respect to each other at constant velocity. So, if in one frame the center of mass is at rest, in another frame it may be moving with some constant or uniform velocity. Let us take a rigid body again. This time its center of mass is moving in this direction, and with respect to a certain axis of rotation, the coordinates of the center of mass, or the position vector of the center of mass, is RCM. And then one can write its angular momentum as mRCM into across VCM, because these are vectors, therefore, we have to take the cross product. More of it in the next lecture. We shall talk about angular momentum. Likewise, the kinetic energy of rigid body can be written as half m VCM square. That's you note the motion of, or the velocity of the center of mass, and then the kinetic energy is simply half m VCM square. We now consider a system of particles, not a rigid body. In rigid body, particles have fixed positions with respect to each other, they do not change. But now we are considering the system of particles, where the particles are moving around and they change their positions with respect to the other particles. So, we have this system, and the center of mass has coordinate r, and Ri is the coordinate of any particle I in that system, and Ri is small ri is the position vector of that ith particle with respect to the center of mass. So, we can write from the vector algebra Ri is equal to Rcm plus Ri. We can differentiate with respect to time and we get Vi equal to Vcm plus Vi, where Vi is the velocity of the ith particle with respect to the center of mass. So, let us write down the expression for the kinetic energy of this system of particles. As you know, it is simply half sigma mi Vi squared, and we have seen in the last slide Vi is equal to Vcm plus Vi. So, we substitute it here, this becomes mi sigma mi times Vcm plus Vi squared, and we expand it. The middle term, notice this middle term is Vcm times sigma mi Vi, which is Vcm dot d by dt of mi Ri, and remember what is mi Ri? Mi Ri defines the center of mass. So, this term defines the center of mass in terms or with reference to the center of mass, and therefore, this term vanishes. You see, the center of mass with respect to the center of mass is 0. Therefore, the second term vanishes and we get the kinetic energy written as two terms. The kinetic energy associated with the motion of the center of mass, that is the system as a whole, and the kinetic energy which is due to the individual particles moving with respect to the center of mass. So, the kinetic energy can be written as two terms. If the system as a whole is at rest, then the first term vanishes and the kinetic energy is simply the kinetic energy of particles of the system moving with respect to the center of mass. We have said that the center of mass of a uniform body of regular shape is at its geometrical center. This implies that it is not necessary that the center of mass be always inside the body. For example, in the case of a ring, the center of mass is at the center of the ring, which is outside the body of the ring. Notice that the gravitational potential, for example, of a uniform sphere is found by replacing the sphere by a point mass at its center. I think this you have done. We assume the earth, you know why we take distances always from the center of the earth, because we assume the whole mass is concentrated at the center, that is the center of mass of the earth, and we define gravitational potential or gravitational energy or gravitational force with respect to the distance measured from the center of the earth, which is the center of mass of the earth. Recall that when we find the gravitational potential or gravitational force of the earth on a particle, we consider the distance from the center of the earth. Why? Because the center of mass of the earth is at the center of the earth. Therefore, what we have done effectively is to replace the whole earth by just one point at its center or at its center of mass. That is the importance of the center of mass. You can get rid of the whole body and you can concentrate on just one point. We also define a point in a body called the center of gravity. You must have come across this term in your books. Center of gravity is defined as the point where the whole weight of the body is concentrated. Students usually find it difficult to relate these 2 points. So, for simplicity, let me say this: if the gravitational field is uniform, then the center of gravity and the center of mass coincide. If the gravitational field is not uniform, then the center of mass and center of gravity are not at the same point. Let us come to the case of the earth. On the earth, the gravitational field is uniform. That means, on the surface of the earth, the acceleration due to gravity does not change much. Therefore, the field is uniform, and on the earth's surface, the center of mass of objects and center of gravity of those objects coincide. They lie at the same point. However, if the gravitational field is not constant, they would not lie at the same point. Let me now sum up the whole thing. Cm is a point where the whole mass of the body can be supposed to act. It is a function of mass distribution. This is very important to remember, that it is not a fixed point, it depends upon mass distribution. It is a function of mass distribution in the body. If mass distribution changes, the center of mass will change. For a uniform body of regular shape, the center of mass lies at the geometrical center of the body, as shown here. It could lie outside the body, as in the case of a ring I shown you. The center of mass is difficult to locate for an irregular body. For a regular body, it lies at the center, geometrical center. For an irregular body, we do not know where it would lie. Here we have given an example of a wax cylinder. The wax was melt and it was reshaped into a sphere, and the center of mass changes, showing that the center of mass is a function of mass distribution of the body. In the next lecture, we take the very important topic of angular momentum and its conservation.